So I'm going to be showing you how to integrate this guy right here. It's a special integral that comes about from solving partial differential equations and having to use the Fourier transform for infinite domain problems. And you have to invert that Fourier transform, so you have to solve integrals like this all the time. And this technique that I'm going to show you is kind of famous, I think, from Richard Feynman. It's called, I was about to say integrating on the integral sign. It's differentiating under the integral sign. Under the integral. And it's very cool. You'll see that it's not exactly like a regular old integral. Anyway, so the first step you do is actually differentiate it. And I'm going to differentiate with respect to x. I can differentiate this guy without too worry because I'm not worried about the integral blowing up or anything. I'm just going to pretend that it's a nice integral. It's not one from real analysis. So I'm going to take my partial derivative in here, and it's only going to act on the cosine omega x term because that's the only term with x in it. And then it's, of course, with still integrating with respect to d omega. So I'm just going to evaluate that now. I get e k omega squared t. That omega comes out. Actually, well, negative omega comes out because it switches sign. Omega x and d omega. Cool. So really what I've done is just kind of set up this integrand. So I've got a derivative here. And what I'm going to do now is actually use integration by parts to utilize what I've just done, differentiated on the integral sign. So let's do by parts. Cool. I always forget the by parts formula, so luckily you can always work it out from the product rule, which is way easier to remember. Yeah, so that's going to be u dash v is uv and then minus uv dash. Well, that's a horrible integral. Cool, so now I'm going to let I'm going to let u dash equal negative omega e negative k omega squared t. That means omega is just going to be the integral of this guy. It's going to be the integral negative k omega squared t d omega. This guy is a pretty straightforward substitution. So I'm going to let this guy, or whatever you want to call that symbol, equal to negative k omega squared t. And then of course this guy, d omega, is going to be negative 2k t omega. And then d psi is equal to, all that stuff is going to come down, so I'm going to have 2kt, and then I'm going to have negative omega d omega. So it's kind of looked after the negative sign there. Cool, I can make that substitution. These two guys are going to go. So u is going to be equal to the integral of e psi d psi, and then, oops, I have to include all the guys out the front. Negative over 2kt, and then that of course is just equal to e my negative k over omega t, like that, and then all over 2kt. Cool. So that's my u. My v was, what was my v? It was sine omega x. And my v dash is just going to be equal to, well, the derivative with respect to omega this time, so it's going to be x cosine omega x. Sweet. Now I'm going to construct this integral, construct this by parts formulation. So it's this guy that I'm doing by parts with respect to. Oops, I'm going to take that with me. this guy right here, and he's going to be equal to, or 2 pi over a bunch of stuff. The first stuff is uv, so that's e negative k omega squared t divided by 2kt sine omega x. Okay, and then it's evaluated at 0 and infinity on the upper limit. And then that's going to be minus 1 over 2kt from 0 to infinity e negative k omega squared t, and then cosine omega x, and we also have an extra x in there, d omega. That x is an invariant under the transformation, so I can take that guy out, put him out the front. Okay, so let's evaluate this. Oops, I closed my bracket. Well, I can see that on the zero, this sine omega x goes to 0. So it's 0 on the lower boundary. That's good, I guess, or something. And then on the upper boundary, well, this guy goes to 0, and it goes to 0 very quickly, actually. And he also squishes this guy, squishes him a lot, and that whole term goes to 0, so that's nice. That is good, so that simplifies things. So then we are left with what? We're left with this. Negative x 2kt, and then 2 pi, and then 0, e negative k omega squared t cosine omega x d omega. Well, that might look a bit familiar to you because, well, it's actually just I. It's this guy exactly here, I. So that's neat. If you remember what we're integrating to, we're actually integrating di dx. And by integrating, we realize that we have to actually solve this differential equation equals I. Oh, cool. That's it's not something you run across every day when you're just walking around in elevators with people and so on. So I guess we should solve this differential equation, which will give us the solution to the integral, which is I. Very cool. Well, I'm going to use the first method in the physicist toolbox, which is separation, the separation of variable technique. So here we just bring all the i's on one side and so on. 2kt dx. I'm going to be integrating both those sides. I'm going to get x squared 4kt plus some constant, and I'm going to get the logarithm of I. I want to undo that logarithm. Oops. So I'm going to take the exponentials of both sides. I'll get I, then I'll get e negative x squared 4kt plus eta. I'll bring that eta straight down. Eta naught, e negative x squared 4kt, just 2. Neat. So this result makes sense. It makes sense because, well, on either side of the transformations, you should be getting functions that are, functions that are absolutely integrable. So if you want to evaluate this, you should not get infinity. And this is exactly, I mean, if that negative sign wasn't there like that, you would get infinity, so that would be bad, and it wouldn't be a valid solution. But since it's there, then since it's just a Gaussian in x, it is absolutely integrable, so that's kind of nice. Very good, very good. Now we have to calculate eta naught. So eta naught is the value when x is equal to 0 for the Gaussian. So I guess we can, actually we have to go back to our old integral up here, and remember these guys are equivalent. So what we really want to do is set x to be equal to 0 in this integral, and that will give us e to naught. So, I mean, that's a cool initial condition. So, if I set x to be equal to 0, x equal to 0, this will equal e to naught. And what will happen here? So this guy will just go to unity. So he'll go to 1. And I'll be left with, well, just the exponential, or just the, just the Gaussian in omega. So cool. That's very good. I mean, I'm happy to integrate Gaussians. They always are nice. And they give good results. They're nice symmetric functions. So we have 2 pi. Oops, why am I writing again? I don't need to do that. I just need to make a substitution here. So I'm going to let, what do I want? What variable do I want? Let's say capital omega equal. Well, let's see. Well, I want capital omega squared to equal that stuff up there. So I'm going to take the root of k and t and then omega. And then d capital omega, d omega is going to be equal to, what's it going to be equal to? Well, it's going to be equal to kt. And then I'll have d omega on root kt is equal to d lowercase omega. All these omegas. Sweet. Okay. So now I have 2 pi over, and also I have 1 over root kt, and I have 0 to infinity, and then I have e negative capital omega squared d capital omega. Cool. So if I integrate a Gaussian from e to negative t squared, I'm going to get root pi. That's something you can prove using polar coordinates. If I'm integrating from 0 to infinity, I'm obviously going to get half root pi because it's a symmetric function, like I said. Root pi on half. Yeah, half root pi. So I can just use my knowledge of the integral to write that down. So I'll get root pi on 2. Those 2's will cancel. What else will cancel? Well, if I multiply by root pi, then I'll have a root pi on the bottom, and then those pi's will cancel. So I'll end up getting this guy right here, kt pi. I'm pretty sure. Yep. Good. Okay. Sweet. So that is actually e to naught. So nice. Okay. Now I just have to sub that in, and then that is it. I is equal to this guy, 1 over kt pi e, and then negative x squared for kt. I think that was right. Yep. Cool. And I guess that's it. So that was a cool integral. I don't know. That was probably one of the coolest integrals I've done for a while.